Okay, well, happy Friday, everybody. We'll we'll get started. This is we're at the end of week 6, so here we go. All right, so I just wanted to spend one lecture covering this package stats models, which is what you would use if you wanted to fit kind of traditional statistical models. And I just thought I would work through, just a simple example, and we'll see where that takes us. Um, and so here we go. Okay. Now, to be honest, when it comes to doing statistical analyses, I prefer using R, and I think it's hard to beat R and some of its functionality and features. You can fit a linear model using LM in R, and it's a very powerful tool, and it comes with all sorts of diagnostic features, all sorts of things that you can do with it. That said, Python has the ability to kind of fit statistical models. And I would say there's kind of two main packages that's used for statistical modeling. And one is scikit-learn, and that's probably the most popular package, especially for machine learning models. So if you want to do any kind of like classification, k-nearest neighbors, whatever you want to do, or even unsupervised learning, whatever it might be, and you can fit linear models with scikit-learn. That's one way to go. Okay. But if you want to take kind of a traditional statistics approach, which is, I would say, where R is really strong and powerful, where you want to fit kind of a linear model, where you want to fit like a logistic regression model, you want to do your kind of traditional analyses, check your residuals and all of those things. Stats models is going to be probably the package that you'll use. Okay. And just like every other kind of package that I'm introducing here, it's going to be important that you take a look at the reference and things like that. In my opinion, the stats models package reference is a tiny bit sparse. They have some good examples, but it will take a little bit more time. In my opinion, it takes a little bit more time to kind of read through the documentation on stats models. Not to take anything away from stats models, but I do think some of the other packages, especially, they have done very thorough job on some of these things. Okay. Anyway, you're going to import. You're going to call import statsmodels.api as SM. That's kind of the way it's done. There's a few other ways to interact with stats models. One is the stats models formula API. This is going to be a little bit more familiar if you are used to R's formula notation as far as creating linear models. The traditional stats models uses kind of a matrix notation approach. And then you can also perform time series analyses with stats models. So stats models is used for, any kind of time series models in Python, and that's going to be the TSA, and you'll import that as that. We're not going to cover that here, and you can take an entire course on time series yourself. My examples today, I'm assuming you have done a little bit of linear regression already, but perhaps that's not the case for some of you. You will do a lot more linear regression stuff in Stats 101A, and so if you've already taken that, some of the stuff will be familiar. If you haven't taken that class, I imagine a lot of the stuff I do here, none of it is truly revolutionary or groundbreaking, but you might not be familiar with some of these ideas, but that's okay. All right, it's just kind of here in case you want to do it. All right, and so anyway, my first thing is just kind of import all of these libraries. So we got import NumPy, import pandas, import matplotlib, import Seaborn, import statsmodels API, statsmodels formula API. Okay, and so what I'm going to do is I'm going to use a data set. And this data set actually comes from an R package. And there's a function you can call called get R data set. And this actually goes to some of the CRAN packages, some of the packages for R, and it will pull out data sets from within there, just because there's some really good data sets in these R packages. So anyway, one of the data sets that we'll take a look at is this, we'll call it the Duncan Prestige data set. And this is something that came from the 1950s. So, 70 years ago, they asked people, they took a list of 45 different occupations in the United States, and they asked people, they asked them a few questions. So one was, well, first they classified them. Is this a professional or managerial job? Is this a white collar job or a blue collar? Blue collar being like you work in a factory, white collar meaning you work at a desk, and professional kind of, you're in management or you've got some kind of professional thing. And then this was the 1950s. So they said, what percentage of these people who hold this occupation, what percentage earn more than $3,500 per year, which I guess is something around the median income around there. And I don't know. This was in the 1950s. I have no idea what life was like back then. Okay. And then they also asked what percentage of people were high school graduates, okay, which apparently wasn't as common back then. And then they also asked, and the prestige is they asked other people in some social survey, is this would you consider this to be a good job? Okay, and so just so you can see what some of these jobs were like, they said, an accountant is a professional job. 62% made over that, threshold, $3,500 a year, I guess. And then 86% of accountants were high school graduates. And when they asked people, is this a good job? 82% of people said, yes, that's a good job, right? So architect, 90% of people said that's a good job. Chemist, 90% of people said that's a good job. Dentist, things like that, okay? 80% of dentists made over this, 100% of dentists and things like that, okay? Yeah, so when you use this thing, this get R data set into Duncan Prestige, it creates this object. And in order to actually access the data, you have to call .data. Now, what I could have done is I could have done get R data set and then called .data here, and then set that to Duncan Prestige, and then I wouldn't have to keep writing .data every single time. But I didn't do that, so I'm just going to call .data every single time, and I think that's fine. Okay, and then so just a few of these other things, like store clerk, only 29% had that. Only 50% of people had finished high school, but only 16%, I guess, considered this to be a quote unquote good job. And there's a few more things like waiter and things like that. So you have factory owner and banker and store manager. This was the 1950s, so who knows? Railroad engineer, these are different jobs. Okay. And so anyway, we can explore a few different variables, right? So we could fit a model where we're going to predict prestige based on education or prestige based on income. We can also just to see is there a relationship between the income and education. And again, income here is, what percentage of people in that occupation make over a certain amount of money, some arbitrary threshold. And then here, what percentage of people have graduated high school in the 1950s. And so this is kind of the plot of education versus income. And so we're going to try to predict income based on education. And so in order to do this, we will extract the column income Okay, and we'll set that equal to y. We'll extract the column education, set that equal to x, and here's just a plot of education versus income. Okay. All right, and so the way the model notation works, okay, is that we're going to do kind of matrix. Basically, stats models uses matrix notation. So does scikit-learn. So scikit-learn and stats models both uses matrix notation, unless you call the stats models formula API. But what we want to do is we want to figure out, okay, what is the slope and intercept? Okay, the slope and intercept is going to be our B0 and B1 terms. So, what we're basically saying is that the predicted income, okay, the percentage for, when we predict what percentage of people make over a certain amount of money, that's going to be based on what percentage of people graduated high school. And then the true value is going to be B0 plus B1 times X, the intercept plus the slope times X, plus some error term, okay? That's the true value. Whereas the predicted value, Y hat, is going to be B0 plus B1X, okay? And we don't bother figuring out the error term, okay? So as far as our kind of vector or matrix of Y hats, this can be written as the multiplication of our X matrix and our B matrix. The B matrix consists of the intercept B0 or beta 0 and the slope beta 1. Okay, and in order for this matrix, the X matrix and the beta matrix to multiply properly, the X matrix needs to be, an n by 2 matrix. We need to have, because we have 2 terms in beta, X needs to have 2 columns. And so that means we're going to have to take our values, our X values, which will be our education numbers, and we have to append a column of ones. All right, does that make sense as far as adding a column of ones to our X matrix? So we have to do that. And so that's what we're going to do. Okay, so and with that, we will have kind of this matrix notation. All right, so we have to add a column of constants, and there's a function in stats models that does exactly this. Just because it's such a common operation, we're going to call add constant. So we're going to call stats models.add constant, and we're going to take our X matrix, and I'm going to save this back to X. Okay, and when I do this, it adds a constant. Okay, and so now if I ask, well, what is X? Okay, X is this matrix or data frame, and we can see one column for the constant, and it's all a bunch of 1.0s, and then we've taken that column education, and we have the values here. Okay, let me I forgot. Let me do the view quiz answer, but I forgot to set it up right now, or I forgot to make it visible. So let me give you your first view quiz answer. First view quiz answer today is the letter C. The letter C as in cat. But let me just, it hasn't been turned on yet. So give me a second. Okay, so your first view quiz should be visible, and the view quiz should be visible, and the first view quiz answer is C. C as in cat. Okay, so here we've added the column of constants. Okay, and so now to fit the model, you call statsmodels.ols.fit. Okay, and so inside, when you specify OLS, you do Y for the values, that the actual values, and then X for the X matrix. Okay, and as far as if you click the API reference, you can see, under the stats models API, which we've imported as SM, these are kind of the regression models that exist. All right, so you have OLS, but you also have GLS for generalized least squares. So OLS is ordinary least squares, but you can also have generalized least squares. You can have generalized least squares with AR covariant structure, weighted least squares, recursive least squares, rolling ordinary least squares, rolling weighted least squares. These are all different options, okay? And you can also have GLMs, generalized linear models. You can also have, if you wanted to fit like a logistic model or things like that. And then you can also specify, logit and multinomial, Poisson, negative binomial, different kinds of models as far as the different models that you can fit. Okay, so here, as far as today goes, I'm just going to do OLS, but here's basically when you go to the API reference, it'll have a list of pretty much all the different kinds of models that you can fit. Okay, and so when you call, whatever model it is, in our case OLS, so if you do model.fit, this result is going to be a dot regression results object. Okay, and this regression results object, there's a bunch of kind of terms that you can get. So as far as the linear model goes, there's a bunch of kind of attributes and methods and properties that are available as far as things, information about the model that you can extract. Okay, so I'll just go over a few of them here, but the reference is on on this page. Okay, so one is you can print out the summary. Okay, and if you call print, it's going to come out in this formatted kind of plain text format. And if you call later on, if you just call summary without print inside a Jupyter Notebook, it will format it looking like this. Okay, this is the same information, but just formatted another way. Okay. Okay, so here you have all kinds of things. You have, the coefficients. So probably the things that you'll be most interested in is the coefficient as far as the constant goes, and the coefficient that gets assigned to education. This would be the slope, and this would be the intercept. Okay, and then you have a bunch of other kind of values and things estimated, right? So here it says your dependent variable is income, and the model is ordinary least squares, and 45 observations, 43, one degree of freedom for the model, just because we have one predictor variable, and if you have a total of 45 observations, you'll have 44 degrees of freedom total, so that leaves 43 for the residuals. You get an R squared value. It also has an adjusted R squared, an F statistic, the AIC, the BIC, the F statistic of the probability or p-value associated with this F statistic. Okay, and as well as for each coefficient, you also get an estimated standard error and the corresponding test statistic and the corresponding kind of p-value. Okay, and so our p-value for both of these things are both less than 5%. So we can conclude that income is associated with education, and that's, yeah, I mean, you've got a bunch of other kind of statistics that can be calculated. So a lot of information is here. If you want to kind of get at pretty much any one of these values, so you can use them in some kind of future calculation, you can often refer to them as well. So if you wanted to get the intercept and use it in a future calculation, you can call OLS model.params, and then you can do square bracket 0 to kind of get this value, or you can do square bracket 1 to get this value. Okay, you can get this R squared value, 0.525, you can get that right here, OLS model.R squared. You can get, any of these, how many degrees of freedom, this number 43, this number 1, those are also available in just OLS model.df model.df residuals. Okay, and again, all of these things are in the API. You just kind of go down to either the attributes or the properties, and it kind of just lists off basically all of the different things that you can extract out of the results there. Okay, so you can call, what are the p-values or the t-values or the sum of squared residuals, right? Because Sometimes you want to use some of these values in some kind of future calculation, or you want to enter it in some other place, and so you can kind of reference those things there. Okay, a few more things. So the t values, okay. So these are from kind of the t-tests here. For the intercept, we have a t-statistic of 2.04. For the slope of education, we have a t-statistic of 6.893, right? And so here it is kind of with more precision rather than rounded off to fit in that table. And then the associated p-values for these test statistics appear here as far as OLS model dot p-values, okay? And keep in mind that this part is the results of fitting the OLS model. So we created the OLS model by calling statsmodels.ols, providing it the data, and then calling fit. And that's going to fit the model to the data. Okay. And then the overall kind of p-value of the F statistic associated with the model here is, we get something on the order of 10 to the negative 8, indicating that this is indeed statistically significant. Okay. You can also kind of just see, what are the predicted values. And so here is the, you can ask for the model.fitted values. And this is going to say, this is what we predicted as far as, our response variable being income. We can say, all right, this is, the proportion of people that make over that, whatever threshold exists there. Okay. You can also, if you wanted to make predictions for new observations and things like that, you can also call OLS model.predict. Okay. So fitted values will give you kind of all of the values as far as the kind of your training data, the data in the set that you use to fit the things. And when you call predict with no values provided to it, nothing inside this argument here, then it's going to give you back basically the same numbers. So, here it starts off with accountant at 61.76, pilot at 55.81. And that's exactly what we have here, 61.76, 55.81. It basically, if you give it no values inside here, it's going to just give you back pretty much all of the predicted values for all of the data that exists in your current data set. Okay, but the power of predict really comes in when you want to predict values for new observations. Okay, and so when you want to give it a new observation, you have to give it data in the same form or in the same kind of format as your training data. So in our case, our training data had a column of ones and a column of X values. And so let's say I wanted to predict the income for an occupation where 55% of people had graduated high school. Okay, again, in 1950. In 1950, we asked what percentage of people have graduated high school in this occupation. And so we're going to say, for this occupation, 55% of people have graduated high school. Now, in order for it to kind of align, it needs to be a 1/2 matrix. Okay, so if I just did this 1, 55, this is not going to be a 1/2 matrix. This is just going to be a length 2 array, right? It's going to be a length 2 array. And so here I'm going to call numpy, take my array, and I'm going to reshape it to 1/2, right? And so now I have a 1/2 matrix, and I can see kind of the double square brackets. I could have also done the double square brackets myself to create it, but here I just did this to kind of just emphasize that it needs to be a particular shape, right? So here's my X new. I can put that inside predict. So we have my model. I'm going to do model.predict. This gives me the predicted value. X new is 43.3. So now if 55% in this career have graduated high school, we would predict around 43% to make over that certain threshold of money. Okay. Here's just another example. You can, let's say if you wanted 3 different things. So here's some occupation where 55% have graduated high school, 20% have graduated high school, and 100% have graduated high school. Okay. What I can also do is I could just call statsmodels.add constant, because that's basically what I did in order in my original data. I took kind of my vector, my one-dimensional array X, and I added a vector, added a constant to it to make it a two-dimensional, or a two-dimensional matrix. And so now I have a 3x2 matrix where I've got a column of ones. And then I can feed this into model.predict. And with model.predict, because I've got 3 values here, I'm going to get back three results. Okay. So the 55 still produces the same prediction, 43.32, as we would expect. We would expect to get the same value, and that's what we do. The occupation with 20%, predicts a lower value, 22.5. The occupation with 100% predicts a value at 70%. Okay, and so there you have it. Okay, so you can use this to kind of make new predictions. Okay. You can also ask for the residuals, as far as the, so you're only going to get residuals for the your training data, the data that you actually have and things like that. And so, so here is the residual as far as what you have. And so you can see, we have a couple residuals where, the proportion in the income is much lower or much higher. So railroad engineer and conductor, the income there is much higher, compared to kind of the education experience. And as far as minister, the income is much lower compared to kind of what the educational experience might be. So if we just kind of look back at the original data. Okay, so as far as ministers go, 84% are highly educated, but only 21% have a higher income. Whereas if you look at something like railroad engineer, only 28% have a high school education, but 81% have a high income. And same with where did the other one go? Okay, maybe that was it. There's railroad engineer and some other thing. Okay, or there was a thing. Okay, but anyway, that kind of makes sense, right? In order for ministers, they usually have to go to, some kind of Bible training seminary or something like that. But it's not known to be a very lucrative job unless you're like on TV or something. But anyway, that's what we have here as far as residuals go. Okay, and so this is what we see, and we kind of want to just conductor, that was what it was. We kind of want to see what the things look like. Okay, so teachers, same kind of thing, right? Generally educated, but generally not making as much as one might expect or something. So we can plot diagnostic plots. So when you fit a linear model, you want to kind of make sure that your residuals appear to be normally distributed. You want to see that your residuals don't follow some kind of pattern or things like that. So here, one thing is here I'm setting some options for the figures. Okay, so because I wanted to kind of get the figures to fit on the page. So we're going to do, I set the figure size here, and we're also going to set the font size here as far as the plot goes. Okay, and so here I'm using matplotlib's functions here. Okay, and as stated earlier, in Python, a lot of these packages rely on matplotlib's plotting abilities and plotting capabilities to produce plots. So here we've got PLT using calling matplotlib, and then RC is for kind of your figure controls. All right, and so just to kind of make some of these plotting functions easier, we're going to take the model and we're going to ask for the residuals, which is basically this, and I'm going to just store it. save it as residuals here. I'm going to say residuals equal that. Okay, and so one, we'll plot the X variable, education, against residuals. All right, and this is kind of the plot. And so, this is the minister where, many people are educated, but generally lower income. Over here, we have the conductor and the railroad engineer, where not as many are educated, but high income, at least in the 1950s. And then we ask, is there any kind of pattern that we see here? And yeah, I don't know. It doesn't look like there's too much of a pattern. It seems okay. I don't know. All right. Here is kind of a QQ plot of the residuals. So you can ask for, a quantile plot, and what you want to see is kind of a more or less a straight line. And so this departs and this departs. And so these things don't quite fit the normal model, or don't fit this, fit a straight line here. And so, yeah, so these would indicate to us that these are true outliers, getting the conductor and railroad and the minister. These are actual outliers that don't quite fit the straight line here. So this is, you can create your kind of QQ plot. And again, this is not a course on regression, but just showing you some of these tools that are commonly used in regression analysis. All right. And then, and again, you can plot do an influence plot. Okay. And so you can get kind of a measure of leverage, and you have kind of the Cook's criterion for leverage and stuff like that. Okay. These are just, the size of the circles are based on basically the residuals. So if the residuals are closer to 0, the circles are smaller. And if the residuals are farther away from 0, the circles are bigger, just to kind of bring your attention to that. And so, this is kind of an indicator that this is what we have. And, as far as leverage goes, these ones aren't super far out, right? So depending on your data set, leverage being kind of, if it's the only observation that's very far out in X, it's going to have a high influence as far as the slope of your model. Or if it's a very value of X that's very low and it's kind of the only observation out in its vicinity, it's going to have a high influence on what your model slope and intercept are. And so that can be measured using Cook's distance and things like that. And so these are tools that are available. Let me go ahead and give you your second view quiz answer. Today's second view quiz answer is B. B as in bear. B. B as in bear. Okay, are there any questions on any of this stuff so far? So far, so good? Okay. All right, we'll probably end up finishing a few minutes early today. But so I just also wanted to show you that you can use formula notation. Okay, and in order to use formula notation, you would call the statsmodels formula API. Okay, and then kind of the tradition is to import that as SMF. And so here I'm going to call statsmodels formula.ols, and when it's formula, it's the lowercase OLS rather than all caps OLS. And so if I go down to statsmodels formula API, there's a bunch of models that are available. These are all lowercase. So OLS is going to be for ordinary least squares, but you can also fit other ones as well. And all of these expect some kind of formula to come in. Okay. But this is it for the documentation. But all of these things, the output is going to be pretty much the same as a linear regression model. Okay, so here we're going to say the formula this time we're going to predict prestige. So instead of doing the same model predicting income based on education, I'm going to compare 3 models. We're going to say, what are people's opinions of prestige? Is it based on education? Is prestige for a job based on income? Or is prestige some combination of income and education, right? So today, you know, what are highly respected jobs? Highly respected jobs probably are things like doctor and lawyer, and those are both high income, high education jobs. Okay, I don't know if data scientist is getting there, but a lot of people, at least a lot of job opportunities exist for data scientists, and that requires a certain amount of education, and I would say it's fairly desirable because there's an income draw there. Okay, and then, you know, as far as other kind of occupations go, perhaps the prestige, you know, when you ask, you know, is that a good job, and whether people say yes or no could be based on things like this. Okay, so anyway, here we specify the data, and again, because I use the import from our data, I have to call Duncan prestige.data. You know, obviously, if you have some data set that you loaded via a CSV file, you don't have to do that. You can load your CSV file and then do that. So anyway, you call set up the OLS model, and then you call fit to fit the data. And let's go ahead and take a look. And so this is our first model. Again, the first model is based on education. The second model is based on income, and the third model is based on both. So based on education, you know, this model only has 1 degree of freedom, and we get the slope for the education and things like that. Okay, and this is significant, et cetera, et cetera. Here's model 2, which is where we used income. Okay, and we get some kind of coefficient there. And so, you know, the more income people have, you know, perhaps more people say that it is a good job. Same thing, or more education people have, you know, people are more likely to say it's a good job. Okay, model 3 being kind of the combination, now we have 2 terms here, income and education. And so here are the degrees of freedom for the model uses 2, whereas the other ones, because there's only kind of 1 additional coefficient to estimate, there's only 1 additional degree of freedom, versus, you know, the null model, where is basically when you have no model, you're just predicting the mean for everybody. So you have one term that you're estimating. So that uses up your 1 degree of freedom. When you have a single predictor, you have two coefficients to estimate, the intercept and the slope. And so that uses 2 degrees of freedom. And so that's 1 more than just predicting the mean only, right? So the model uses 1 additional degree of freedom versus predicting the mean only. And therefore, you know, your residuals, you only have 43. Over here, we're predicting 2 more. We have a slope for income, a slope for education. So we have 2 additional degrees of freedom used by the model, and we have 42 left for the residuals. Okay. And so if you wanted to compare models, so for example, if you wanted to compare model 3, which uses 2 degrees of freedom, versus model 1 or model 2, you could do that directly using an F-test to make that comparison. You say, is the more complicated model, the one that uses 2 degrees of freedom, is it giving you better performance than the one that uses only 1? Okay. Oh, there was a question, do we need to add a constant? So when you do formula notation here, you don't need to add a constant. Okay. So you do, you just write it like this, prestige tilde education. And this should look kind of familiar if you're coming from R, if you've used the LM thing, and this will create, this is made to kind of be familiar for those people who are coming from R. This should look like a familiar interface, and you don't need to specify a constant there. Let me see. Formula object. Formula. Let me see if there's a rule regarding how to write formulas. I don't know where it is in the help. Okay, so anyway, this exists, and if you want to compare kind of one model versus another, you can say, you know, let's do model 3, compare it against model 2, right? So model 3 versus model 2, model 3 has this, and it's you know, its R squared is 0.828, and oh, it's not listed here, but we could get the kind of residual sum of squares. That's going to be somewhere, and we could do kind of the calculation and see, you know, is the improvement in the RSS, reduction in our residual sum of squares, is that improvement worth the additional degree of freedom? And so, you know, we're going to compare model 3 versus model 2. And when we do that, the F ratio, the F calculation, that statistic is 30.8. And this second value is the p-value. Okay, so the p-value comes in at around on the order of 10 to the negative 6, indicating it's a very significant p-value, and saying that this additional 1.0 additional degree of freedom, the additional degree of freedom that you use, it's worth the extra, it's worth the cost in degrees of freedom, right? Because in general, you know, as far as traditional stats linear models go, you know, you can always make your model more and more complicated. And every time you make it more complicated, you're using up a degree of freedom, right? And so you get kind of a degree of freedom budget based on how many observations you have. So your total degrees of freedom is going to be number of observations minus 1, and every additional parameter. So every kind of variable that your predictor variable you're using uses up an additional degree of freedom. Every kind of interaction term you're predicting uses up a degree of freedom, et cetera, et cetera. And, you know, if you have too many predictor variables and only a few observations, you could end up using up all of your degrees of freedom, and then your model is, I forget what the term is going to be called, but basically you get, you know, a singular solution, and you can end up predicting every single value perfectly. And that's not going to be a good situation. Okay. And so basically every time you add an additional predictor and you're using an additional degree of freedom, you want to kind of ask, is it worth this additional degree of freedom? And so that's a question you can kind of ask. And so you can use the F test to make that comparison. And so here, this is the test, the p-value. And so to go from income and adding education in there, that's going to increase this, and we get 10 to the negative 6. Comparing model 3 versus model 1, we get an improvement, and it's significant. We get a p-value of 10 to the negative 5. Okay, so so they both kind of perform better. You know, if I had a different data set, you know, maybe I could show you an example where, you know, adding an additional predictor would not improve the model significantly there. Okay, so, you know, that's just the basics as far as stats models go. If you do want to do more, I would just suggest that you check out the reference, and there's going to be, you know, quite a few examples as far as different things that can be done, and, you know, what kind of plots you can create, and if you need to do some other form of regression or some other model to fit. Okay, we'll wrap it up here, and let me give you your last view quiz answer. Last view quiz answer for today is A as an apple. A as an apple. I have posted homework 4. Homework 4 uses pandas and has you do some summaries and stuff there. So do practice with that. And other than that, have a good weekend, and we will see you guys on Monday. I'll see you then.